everything changed. Everything changed. This is a very different talk for me. In fact, I've never given a talk like this. This is something that's very important to me, and it's research that right now I need to know the top researchers in this area, and that's systems of dependent degrading components. And so today I'm doing this work anyways. I need to do this work for some of my current research projects. So I'm assembling all this material. And so when I was asked to give the seminar, I thought it would be a good time to share. I have, like I always do, I have more slides than I have time for. I apologize for that. I tend to, when I prepare a presentation, always say, well, one more thing. And then, of course, I likely won't have time for it. Here's my talk today. I'm going to spend maybe too much time, but you'll be the judge of that. Motivating the problem, trying to tell you that it's important, and defining the problem, as opposed to just giving some analytical solutions and models. So I'm going to spend about 25% or 20% just introducing the problem, types of dependence and effects of dependence. I did some simulations in the last few days so I could show you. I'm going to try to do a simulation, while I'm speaking. It may not work, but I'm going to try. So first, what do we even mean? Dependence, depend. It's a word we all use. This depends on this. Independence, dependence. What do we really mean by this? And in engineering anyways, and in reliability, there can be three different interpretations or three different meanings of dependence. One, which is obvious, is economic dependence, meaning there's limited budget, there's limited money. If I spend money or budget to repair or maintain one component or one part of the system, there may not be budget for another one. So decisions I make for one component will affect decisions I make for the other. Economic dependence. A subset of that would be logistical dependence, meaning there might be limited spare parts. There might be limited equipment in order to do a repair. Now, the second form of dependence would be functional or physical dependence. When you talk to a mechanical engineer, and by the way, I have a degree in mechanical engineering from Cornell University, so I started my career as a mechanical engineer. When you talk to a mechanical engineer and you talk about dependence, this is what they think you mean. They think you mean physical dependence. This affects this. This failure depends on this failure. And by the way, that could be right. That could be right. When we say functional or physical dependence, it's some sort of a cause and effect. This happened, this degraded, it causes this to degrade. So that's functional or physical dependence. When I talk and meet with mechanical engineers, I have to be really clear that while this could be the issue we're talking about, it is not necessarily, because the third category is stochastic dependence. This is mostly what I'm interested in. This is mostly what I'm interested in. We have random variables. The random variable of interest here is a degradation measure at a particular time t. And there's some relationship between those random variables. And such that if one is higher maybe than we could expect, the other one probabilistically may be higher, or the reverse. Now, why would they be dependent? Well, lots of reasons, lots of reasons. There may be some external variables we don't even know about that are influencing them. Maybe they are functional or physical dependence, or maybe each of those, as they degrade, influence some third factor that then influences both of them. Now, how do we measure, or how do we observe stochastic dependence? Covariance. I typically use covariance, or you could do correlation. So the first equation at the bottom is the covariance between two times to failure, T1 and T2. The second equation, they're just general equations, is the covariance for two degradation measures, X1 and X2. And if the covariance is greater than 0, it shows dependence. If it's significantly greater than 0, it shows greater dependence. The covariance is measured on the same scale as the variance. The correlation coefficient, on the other hand, ranges between -1 and +1. Now, so I'm interested in this form of dependence. Now, this is a simulation I did actually just recently, I think yesterday, because I wanted to demonstrate, and maybe, so imagine these degradation paths, and so this is a degradation measure versus time. When it reaches that threshold, it's a failure. So the distribution of when the lines cross the threshold, that's our distribution of failure time. Now, imagine this scenario. See that little system, component 1 and 2 in parallel? They both have normally distributed failure times. One has a mean of 200, one has a mean of 220, and they both have a variance of 20 squared. So the standard deviation would be 20. But the covariance is a variable. So I conducted simulations. First, this is T1 versus T2. This is 35 simulated data points. This is with a covariance of 1, which is a correlation of 0. Keep in mind, covariance has the same units as variance. So variance here you see is 400. Now I've increased it to 0.36. Keep in mind the variance for T1 and T2 is the same. I haven't changed it. Now this is increased. You start to see, again, this is just 35 data points. You start to see some pattern. Now I've increased the covariance 16 squared, or the correlation is 0.64. And finally, we can see the dependence pattern, very clearly, T1 versus a T2. What I was going to do, and I hope this isn't a mistake, please, what I was going to do is show you my simulation. If this doesn't work, All right, this is, I developed yesterday this template. And so this is with no, everyone is 35 data points simulated. This is with no, or essentially no, covariance. So they're random, T1, T2. Now, I'm hoping you can see that okay. In yellow, I'm changing the covariance. And now I've changed it such up to 100. And so, okay, you can, you can see there's some, not always, some pattern. Let's increase it again to 200. Yeah, you can see it, and let's increase it one more time to 300. So what's my point? My point is, well, I kind of want to show you this cool Excel template I did to do this. But my point is, the covariance is our measure of that. Let's move on. Now, still motivating, and I got to watch the time. And I'm trying to make this talk for a general audience. What are some forms of dependence that I think everyone, even if they don't study reliability, would understand? One is common cause failure. Do you know what that is? Look at this. Look at the diagram. Component 3 just failed. Oh, there's component 1 failed. Component 3 again. Component 1 again. Component 3. Now watch. Ouch. A common cause failure. All the components failed simultaneously, or a subset. What would cause that? Some external shock. Some external shock to a system that simultaneously causes many failures. If you don't realize, if you haven't thought about it, that will lead to dependent failure events. Look at these 3 graphs. This is for the system with 3 components, 1, 2, 3. Graph 1, T1 versus T2. Graph 2, T1 versus T3, T2 versus T3. I'm changing the frequency with which common cause failures occur. When a common cause failure occurs, all the components fail. Now, they may fail before that. So now watch. This is very infrequent common cause failures, but I'm starting to increase it. I'm starting to increase the rate with which it comes. With common cause failures, if you see the dots along the diagonal, that means it caused several of them simultaneously. Let's increase it again. Yeah, it didn't even, it actually looked better. Let's increase it again. Now we're starting to see a pattern. And finally, this is the event when common cause failures are happening a lot. You see the dots on the diagonal. That's when a common cause failure is causing simultaneous failures. What's another example? Load sharing. The example people like to use is an elevator with the 3 cables. Watch my picture. 1 fails. Now, what happens when 1 fails? It puts greater load on the other 2. And they're going to then be more frequently, they're going to fail more frequently. And what happens when the second one fails? The third one carries all the load. Well, there's many, many models for load sharing. I just picked this simple one here, that whichever component fails first, in this instance, all 3 components have a Weibull time to failure distribution. And whichever one fails first causes the Weibull scale parameter to decrease by 1 minus alpha on the other ones. So now watch this. This is first, look on the far right, alpha equals 0.1, which means it hardly changes. You don't see much pattern, but now alpha 0.3, alpha 0.5, you're starting to see the dependence relationship. 0.7, look at that. Look at that. So what does that mean? When 1 component fails, it could be any of the 3 cables, the characteristic life, or excuse me, the scale parameter drops to 0.3 of what it was. Well, when that happens, the second one's going to fail very quickly. And when that happens, the third one will fail very quickly too. So another form of dependence. Now, why do we care about this? Most people, when they take a class in reliability, the professor, almost from the beginning, talks about the independence assumption. In fact, so many people who work in reliability, they think in their heart, a series system, you multiply the component reliabilities together. They were taught that. They believe it like it's the truth. And it is true, but only if the events are independent. It's not true if they're not independent. Look at the parallel system upper right. The equation on the left, that would be the equation if they are independent, those 4 components. The one in the middle would be the system reliability considering dependence, and that's greater than the maximum. So what does this tell us? This tells us that if we make an independence assumption, we're optimistic. We think it's better than it really is. And I think that's pretty obvious, because the whole idea of redundancy is if one fails, you have the other one, and then the third one. But if they're dependent, if one fails, the other one might be very quick to fail too. So you lose the benefit from the redundancy. Most people can understand that. Series system is the opposite. Look at the equation again. On the left, it's the reliability computed if it was independent, and that's actually lower than the system reliability considering the dependence, and that's lower, which is obvious, than the minimum. So if you incorrectly assume independence, and quite frankly, often it is independent, don't get me wrong, but if it's not independent, you're actually being pessimistic. You think the system reliability is worse. Now, some of you know me, as it was said in the introduction. I have some, 100, some more than 100 papers, and many very well cited. Most of my papers are optimization, and my teaching is optimization. This semester, I teach 2 classes in optimization, a nonlinear optimization for PhD students and an applied optimization for beginning master's students. So my interest in this area of degradation models often relates to how it impacts a optimization model. Look at that formulation I have there. I'm maximizing system reliability, capital R. I have 2 constraints. X is a vector of decision variables, could be anything. Now, my goal is to maximize reliability. This is work I've done many times. Let's say that's our optimal solution. But that's our optimal solution, assuming independence. What if then we change the reliability to consider dependence? The optimal solution will shift. As the covariance increases, the types of solution that will be optimal will change. There'll be less redundancy, and we'll be using more reliable components because we don't get the benefit from reliability. And if the covariance increases again, we'll have designs that look more like that. And a lot of people already know that. When you compute these redundancy equations, you show this very large reliability, but it might not be real if there's some dependence relationship. In this diagram, the size of the component represents how reliable it is. So 1 isn't always the same. That just means it's in the first position. Okay. Let's move more quickly because I'm going to run out of time. So if we have a dependent relationship, how do we model it? One common way is a Markov chain. This is now just 2 states, failed or not failed, with 3 component system. If, as you move from state to state, if the states in the circle there, like 0, 0, 0 represents nothing failed. And then we move from the different states to show component failures. If, as we move on this Markov chain upward, the transition rates lambda increase, we'll have a sign of dependent failures. Of course, I could have repair rates too, but I'm not shown in that diagram. What's another way? Well, I could just have a joint distribution function. Like for the example here, I have a bivariate normal distribution with two failure times. Here's another example, a bivariate Birnbaum-Sanders distribution. Okay, so if I have a joint distribution function, and often I don't, but if I do, I can compute the reliability. Well, generally we don't. So we're going to approximate that joint distribution function by a Coepolar function. And that's in our talk today, that's one of the major topics we're going to address. So what is a Coepolar function? Look at the equation, f of t, t1, t2, t3. That's the joint distribution function for failure times. If they're not independent, it's not the product of the marginal distributions, but we can approximate the joint distribution as the product of the marginal distributions. You see that on the first equation, then multiply by this Coepolar function. That's a nice, convenient method, and there's many different choices to pick, which is both good and bad. good because there's different choices, bad because we don't necessarily know which to pick. Now, this we'll do really quick. Degradation. We're looking at some performance measure that's deteriorating with time, and we're going to put a model to it and track its performance against the failure threshold. We think about how reliability is studied. There's a traditional approach: collect failure times, fit a distribution, assume homogeneous populations. There's also physics of failure approaches. Today, though, we're talking about this degradation model. We have some observable and measurable loss of performance, and we're going to fit a model to that and use it as our reliability. Many benefits. One is I can collect more data as opposed to just a failure event. And then for my purposes, and I think some others, I can use the degradation model, even if it's a Markov chain, but certainly a stochastic process for condition-based maintenance. It's a much better tool, much better analytical tool than, say, a failure time distribution. Well, what actually behaves this way? Well, lots of stuff. Wear out, corrosion. I showed this one specifically because that's Zhanhang Li right there in our civil engineering lab. One of my primary research efforts now is the reliability of these rebars, which you see in the picture. A rebar is used in a bridge, a bridge for roads or trains, to reinforce the concrete and to make the bridge reliable. And so we've been studying this for the last several years, and we fit degradation models to it. And then the bridge becomes a system of degrading components. So this picture is what we've been working on. That's our civil engineering lab there, where we're testing these rebars under many different conditions. Concrete degradation, metal fatigue. I show this one too, because this was some testing. This is for a stent. You know the English word stent? It's something that goes in your body to keep your veins from closing up. And as part of one of my research grants, we had some stents donated to us, and we conducted testing. Battery degradation. Now, given these degradation, how are we going to fit those? We have a general effects model, a random effects model or general path model. We have some function, maybe based on physics. Often it's just linear. And we have vectors. A vector of fixed effects, which are common for all units, we need to estimate. But then a vector, which is random for the ith unit, and that variability will show. So here's some examples. These are just simple examples. So let me go back. If you have a random effects or general path model, we simply fit typically a deterministic function, but then there's the variability by the parameters. But for a set value for the parameters, it's just some deterministic function. So here's some simple examples. The first one on the top, example 1, we have a linear degradation path, fixed y-intercept, but a variable slope. The one on the bottom, they're both variable. Now, here's some examples. This shows both the power and the weakness. For those simple linear curves, for some combination of those random variables, it's showing a straight line. That might not be realistic, but when you consider the whole population of those, it probably has a pretty good curve. Next, I just talk about for 1 second, because this leads to the next, a compound Poisson process. Shocks are coming to the system. Each shock has some damage size. And the degradation, if you look at the graph, is the cumulative shock size, or the sum of the different shock sizes. Of course, the number of shocks, capital NT, is a random variable. But as the frequency of shocks gets very large and the size of the shocks gets smaller, that becomes a gamma process. For most of my research, this is the model we've been using. A gamma process is a monotonic process. This picture shows it to be linear. It doesn't have to be. that for any 2 points in time, the change in degradation will in fact be a gamma distribution. Here's an example where it's nonlinear. Next, a Wiener process. I never get that quite right. This would be a non-monotonic. If you look at the equation there, we have a standard Brownian motion. And look at the graph on the right. That's not the graph of the degradation process. That's the graph of a Brownian motion. So you've got that variability added to typically some drift parameter. In this form, the drift parameter is mu. The sigma is a diffusion parameter. Now here you see it's not monotonic. Notice the degradation for the red line goes above the threshold, but then back below. So we need to worry about the first hitting time of this process. Okay, some more. I'm not as familiar with this, the inverse Gaussian, but as many know, there's been popularized a lot lately. Zhanhang, other researchers have published lots of papers. Geometric Brownian motion is another one. So there's many. Now, finally, and that went longer than I was hoping. What if I have a system? What if I have a system? And the system is multiple components. They're each degrading. Now, other people have studied the issue of one component, but multiple performance measures. And mathematically, we often treat them the same or similar. So now, dependent degradation paths. We're going to see there's multiple different approaches. And this is what I'm doing. I'm comparing them, or not. I'm reviewing them and somewhat comparing them as well. Markov chains, joint distributions, Coepolar functions, shared shock exposures. One of my reasons for giving this talk is to address this one in the middle here. Dependent random effects, stochastic processes. I published a paper on that recently, and I'm trying to promote it. Okay, first, just quickly, Markov chains. Now, although the degradation itself might be continuous, but we've discretized it or put it into specific states. And the components are transitioning from state to state, from good to bad. But there's n components. So if we have n components and each component has m states, we've got a big Markov chain. We've got a big Markov chain. In the diagram you see, or the table you see in light blue on the left, this would be one state, 1, 2, 1, 0, 0, and it's transitioning to another state. What are Markov chains really good for? Lots, as we all know. One is it's good for imperfect maintenance, because a model with imperfect maintenance, you can return not to the original state, but to a lower state. It can also be useful for determining on-condition maintenance if it's at a state prior to failure. Now, what's not so good? Well, first of all, how do Markov chains even model dependent failures? Well, as you advance through the chain, the transition rates increase. In other words, as some of the other components have degraded, the rate with which a particular component degrades even faster could go up. And when that happens, we have dependent failure times. Here's some examples here. This is, we're transitioning with exponential distribution, so it's a continuous time Markov chains. But as we advance up the chain, or as more components fail, the transition rate increases. So you can see on the left, there is no dependence. On the right, there's a lot of dependence, meaning that as other components fail, the rate, and I don't mean fail, as other components degrade, the rate at which it will advance to a more higher degraded state will be much higher. So what are Markov chains good for? As I said, many things. We have a proven, we have many methods to use. What are they maybe not so good for? Well, if you have a lot of components, it's going to be tough. It's going to be tough. You've got a lot of transition rates. You've got to determine what the states are. If you have one or two components, and maybe somebody disagrees with me, that's fine. But as the system gets big and the number of states get big, the chain gets big and difficult to work with. Now, I'll do this quickly because this is my work, the shared shock model. And really, it's not what I'm interested in anymore, but because I did the work, I'm going to share it for about the next 5-10 minutes. So what do I mean by this? A shared shock exposure model. You have a system, multiple components. The multiple components are degrading in two ways. There's a continuous degradation path, like we've talked about, gamma, or general path, or something else. But also shocks are coming into the system. Look at the diagram. On the bottom, we see shocks coming. But whenever a shock comes, look at the bottom, you see W1. Now look up. At the same time the shock comes, there's an incremental shift in the component degradation X. Well, the shock affects the system. In other words, individual components are only experiencing shocks because the system. So every component experiences the same number of shocks. So the number of shocks is a random variable. If the number of shocks happen to be large, every component will get more shocks. Every component will get more of those incremental increases. That's what creates the dependence. That's what creates the dependence relationship. I have a bunch of slides here. I don't need to go over them. See, the shock comes, actually the system should be sitting still and the shock should be the one that's moving, but whatever. The shock hits that system and every component experiences it. So they all shift at once. And that's what creates a dependency. Because in the shared shock exposure model, the continuous degradation without the shocks is still assumed to be independent. So that's actually, even though I wrote these papers with my colleagues, I don't want to spend too much time. This is the first paper we wrote. Again, we wrote papers before this, but this was the first paper for a complex system. 2014, Sanling Song, my student, Qianmei Feng, and Peng. Now this is a shared shock process, but the component degradations are the random effects or the general path model. Then in 2019, we did something very similar, but now my co-authors are, well, some of the same, but Nooshin Yousefi is the first, who's one of my more recent PhD students. But now we have an underlying gamma process in addition to the shocks. And furthermore, we did much more optimization. We determined on-condition thresholds individually for the components. Now, both of those papers, and both of them, certainly the Sanling Song paper has been referenced now a lot. So many people have continued to extend it and work on it. But both of them are extensions from this paper from 2011. Peng, Mei Feng, or Qianmei Feng, and myself. And I'll explain, this is just for one component, but the component has competing failure processes. And in the system level paper, we took this one component and then extended it up to n components. So just each component, this is just one component. It can experience soft failure. We use this term soft, and it gradually increases to failure, or hard. These are competing. Now, why are they dependent? It's not clear. They're dependent because as the shocks increase, the likelihood of either of these failures will increase. More shocks, more likely for a hard failure. More shocks, also more likely for a soft failure because of the incremental change. And so for the device to survive, we have to have both no hard failure and no soft, but those shocks influence both. Okay, hard failure is easy. Each individual shock is just what's the probability it's less than the threshold. What's not easy necessarily is how many shocks will there be? Well, it'll be a Poisson random variable. So the soft failure, which we call, it's the sum of two things. The continuous degradation, and again in the Sanling Song paper, it's a general path model or random effects model, and in the Nooshin Yousefi paper, gamma process. But if you look at the equation, it's the continuous degradation plus the incremental sum of those shocks. Okay, now up to a system level. This is for a series system. For the system to be reliable, component one has to survive. How? It has to survive all NT shocks, and the degradation amount must be less than the threshold H1. And notice it's intersect. Are these independent events? No, they're not, because the NT affects all of them. In other words, NT, which is a random variable, is going to influence all of those. So those are not independent events. But, and we'll skip the math, I can condition. I can condition on the number of shocks. I can sum on the probability of a certain number of shocks as a Poisson distribution. It becomes conditionally independent, and I can compute the reliability. And this is, I don't know. I think this is one of the best equations we've produced, my group of researchers. I guess it might look confusing right here. I'm summing on the shocks. This is for a series system, but I can do it for any system. And taking the product, I have the cumulative distribution function. And then in the middle, you see the convolution integral. That's the cumulative distribution function for a gamma distribution. And I'm conditioning and integrating over the sum of the shock sizes. Not too confusing, too confusing. Here's an example. The dependent reliability is much higher than the independent. Why? Because the shock influence was great. This system, the degradation was mostly due to the shocks. But this shows there can be major difference. In Nooshin's Yousefi's paper, we determined an on-condition threshold. We took the reliability, put it into three regions: safe, aged, failure. We want to do on condition when it's in this aged region. So we computed a cost rate based on inspection costs, downtime costs, replacement costs. Did a lot of the calculations, the expected value. This, what's circled in red here, is the cumulative distribution function for the whole system, that just one component is greater than the replacement threshold. But the replacement threshold is our decision variable for on-condition maintenance. So this was a difficult problem. We did a nonlinear search. This shows the result of the search. On the left, it's the on-condition thresholds, which are decision variables. On the right, the inspection time. So it converged. It converged. Okay, we've extended this several times. This is one extension, distinct component shock sets. What if it's not just one type of shock? There could be a thermal shock, a mechanical shock, a voltage shock. This is, and here's another extension, 2016, where we show the shocks themselves, the shock magnitudes, have a dependent relationship. All right. So those were some of the papers I've done, but I'm not interested in working on them anymore. I mean, if someone wanted to work with me, I would. Because we got more important issues. We got more important issues. Now, one is a joint multivariate distribution, meaning instead of a distribution for failure time for the event. So here's one paper with my friends from City University of Hong Kong. This is I like this paper. This is, no, I don't have the year, 2021. This is an interesting approach. We have degradation, but the degradations are going to be dependent. So here we can compute directly a joint distribution function. So you'll see many of these papers, you see the names like Bin Liu from Scotland, and of course we see your colleague at Tianjin, and then later you'll see Yili Hong from Virginia Tech. These are some of the most productive researchers on dependent degradation paths. This is an interesting one. It's kind of a straightforward one. Similar, we generate 3 independent gamma processes. See them here, Y? But we sum them together. No, I thought I had an animation. So we create 2 different degradation paths, X1 and X2, but they both include this YU term. So the dependence, just like the shocks for the shared shock model, as this random YU term, as it varies up and down, both X1 and X2 will vary accordingly. And with that equation, you can simply determine. It's a convolution integral again, like my shared shock model, but you can derive directly a joint distribution function for the degradation measures. And of course, reliability, you would have to integrate up to some time t. Now, where's t? Keep in mind, as time goes on, the whole distribution shifts. So where's t in this equation? Well, you got to look for it. You got to look for it, but it's there. It's there because the density functions are unique for the particular shape parameter, or I guess that would be a scale parameter for the gamma. So this is a really good example. There's no Coepolar function here, unless I somehow misinterpreted it. We just have a joint distribution. Here's another one. This is with Yili Hong. I don't, I tend to use the names of the people I know. I don't mean to discredit the other names. And of course, Jishang Yi. This is, I think, a really good paper, 2021, Technometrics. But this is a general path model, which kind of makes sense because Yili Hong's PhD advisor was William Meeker, who I think it was, who developed this model many, many years ago. But you have in this model this parameter omega. See it there? So for each of the degradation paths, it's for, oh gosh, I forget which is I and which is J. I think J is the, I is the particular member of the population and J is the particular unit. But these W's are multivariate normal. They're multivariate normal. They have covariance among these, not W, omega terms. If we conditioned on this omega or treated them as fixed, then we would just have independent degradation paths. But the dependence is built into this. So I think this is a good paper. Now, there was other papers. The papers I demonstrate, I'm presenting them as good examples. I'm not saying they're the best examples. They're good examples. A lot of papers, although not, well, actually not that many. When you consider populations of degrading components that are dependent, there's actually not that many papers, in my opinion. Okay, now what about a Coepolar function directly on the degradation measure? Again, again, if hey, somebody's radio's on, please mute. If, okay, I'll just keep.
So what's the problem? What's the problem?
Okay.
So if any ad is opening up from the software from Move.
Okay, I'll just keep going on. Somebody can shut that noise off. Okay, here's one of the best papers. Once again, Yilei Hong. I'm just going to check. It's not me that's making that noise, is it? This is a really good paper. Rung Pan, Yilei Hong. It's a general paper. This is a paper, if you want me to recommend one on Coepolar functions, because it's general. It's for and it's for a general Coepolar function.
Can we pause a little bit? I will try to fix the pause.
Sure.
OK， 何老师，他这是怎么回事？他这个是我这边出来的声音吗？还是
杜姐，你可以找到那个李静是吧？然后你把它
哦，是他那边是吧 ？OK，
对，你找到他，然后把它静音啊。
OK， 好的。OK， Professor， you can go on. I think there's a meeting member there having some problem.
Yeah.
Well, sorry about that. Yeah. OK.
Usually you can mute somebody if okay. So where were we? Keep in mind, a Coepolar function is used to approximate a joint distribution function. So if we back up, we had a couple papers. Here we had a joint gamma distribution. This was a little bit different. This paper, we have a multivariate normal on this omega term. But if it's not clear, we've got all these degradation paths, but the omegas are random variables. So as they go up and down, all the paths will be affected accordingly. So they'll go up and down in a group. The Coepolar functions, okay. Here's a good one. This is just general guidance. Rung Pan, I don't know the first author, but Yilei Hong, he's written, I view him as probably certainly the most accomplished researcher working in this area. Here again, our friends from City University of Hong Kong, and now my host here. Here's another paper that has, I forget now, I think there's a choice of different Coepolar functions. A lot of these papers, I guess I haven't been saying because are optimization type papers, and maintenance optimization. Here's one I just saw. I kind of, although it's actually older than some of the others, but I just saw the first author, Dan Shu. She was a visiting researcher at Rutgers, and of course, my colleague at Rutgers, El Sayed, is one of the authors too. So I took a look at this one, and this is a little different. The joint distribution function and the Coepolar function is on these performance indicators as opposed to a component degradation. So again, use of the Coepolar, Vine Coepolar dependent degradation paths. Here's another brand new paper. Two researchers from China, two from France, condition-based maintenance, published, already 2022, reliability, engineering, system safety. This is, I've just looked at this briefly, I'll be honest, but this is an interesting paper because look, watch my animation down here. We have a system, a complex system, and we have certain components that are strongly correlated. But then among subsystems, we can have loose correlation. So it's a good model. It's a complex model. I don't know all the details, but they used the Coepolar function to model these nested Levi-Coepolar. And so you have some components strongly correlated, some are weakly correlated. So among a subsystem, between subsystems. So I thought this was interesting paper. Wenjin Zhu, Haiping Li, a few other researchers. Look at this diagram. These are the different degradation paths, and you see subsystem 2 in the gray dotted line. Those are correlated. Now keep in mind, correlated or dependent doesn't necessarily mean they're the same. It just means they increase and decrease in a sense together. So they have this model and a very kind of robust maintenance policy, when to do maintenance, when to, what type of maintenance, etc. Now, next, I'm saying this random effects stochastic processes. Now, what do I mean by this? First of all, what's a random effects stochastic processes? A stochastic process has different parameters, a shape parameter, a scale parameter perhaps, or wait, for a process, it could be something else. But the process parameters may themselves be random variables. And if those random variables among the components have some dependent relationship, then the degradation paths will be dependent. Now, that general path model I showed you with before is kind of this too. So sometimes it's hard to categorize, but I did my best. So we have stochastic processes. The parameters themselves are random variables, usually just one, but they share some relationship. Here's a paper, 4 authors, I think they're all different universities, 2018. Look at this simple model. We have a Wiener process. The Wiener process has diffusion, like before, sigma. It has a drift term, which would be beta, but the drift term is multiplied by this parameter alpha. Notice, alpha has no subscript. In this paper, S is the subscript for component. And yet alpha is a random variable. It's normally distributed. This is just for, I believe, a bivariate. So two degradation paths, Wiener. So this is what I mean. We have some random variable, and it's influencing all the components. And so it's causing this dependence relationship. The Brownian motions are independent. Now, here's another one. You know, Yili Hong, Bill Meeker. Now, this paper is just a survey paper. Big data and reliability applications, the complexity dimension. But inside this equation, there's this interesting equation that you see right there. It's very similar to the last paper, but the last paper was just bivariate with one parameter alpha. Now we have these omega terms. And every component has their own omega, but the omegas have a joint distribution. And what Yili Hong is recommending is he has a Coepolar function for those. Now, I like this very much. So I contacted Professor Hong. I said, well, you know, this is 2018. You know, what now? What have you done with this? And he said, nothing. I'm still working on it. And I'm still working on it. So this paper just presented the model. There was actually no results, but I think a good example. Okay. I'm running out of time. I told you I had too many slides. I always do. One of my main reasons for presenting today is to promote my own paper, this one. Dependence considering clusters of components. Again, it's a random effects stochastic process, a gamma process this time. And because we're running out of time, so here, the components are in clusters. So it's different. This is a different, this is something completely new. Some of it's the same. What do I mean by a cluster? There may be 2 or 3 clusters of components that are behaving similarly. Look at these graphs. This is the same system with 4 simulation runs. Components 1 and 2, notice sometimes they're low and sometimes they're high, but they're always together. That's what I mean by a cluster. Components 3 and 4, now they tend to be low, but they're together. So we see components are behaving in these clusters. Now, here's how I modeled this. This is a 2020 paper. It's a gamma process with a very traditional scale parameter. But the shape parameter, this theta parenthesis I, is a function of all these random variables, theta 1, theta 2, theta k. And each of those has a distribution. There's 1 theta for every cluster. Now, my paper is hard to read. I kind of wish I could rewrite it. It's very mathematical, difficult to read. I wish I made it easier. But sometimes when you're writing a paper, you forget that not everyone is as interested as you are. So I made this general for K clusters. In practice, there's not going to be more than 1 or 2 or, But anyways, the variability in these thetas causes the dependence. See the alpha terms? That's the sensitivity parameter. It tells you, is each component in that cluster? And imagine 4 components. These are hypothetical. I've computed correlation coefficients. Look at the one on the left. I've got 2 clusters, 2 distinct clusters. Correlation coefficients are high. 1 and 2 are together, 3 and 4 are together. Look at the one in the middle. I've got 2 clusters, but component 3 is in both. So it gets affected by how 1 and 2, but also 4. Third example, it's all. Let's skip the math. This gets pretty messy. Those thetas are random variables. I had to condition on those and integrate. So it becomes, see that's what's causing the dependence right here. And I got this equation, which doesn't look bad there. And this for a series system. And then the reviewer said, well, what about parallel? I said, well, we can do that too. We can do that too. All right. This is an extension with shocks. And this, I like this to the left because this shows, unlike some of the other papers, the distribution on that theta could be, well, it can't be anything, but it could be many things. This shows it could be uniform, it could be normal, it could be Weibull. Now, the equations are difficult, have to be solved numerically. And then you see the lines on the top are for parallel, the dotted lines are for series, same 3 components though. I don't know what happened to the blue line. All right, almost done. So my paper, that paper came out in 2020, just recently, made me happy. In 2022, there's an extension that's actually better than my paper in certain ways. This is from Zhanhang University. They did a much better job fitting the distribution parameters, and they also gave better advice on how to determine the clusters. My advice was just to determine the clusters empirically. Let the data tell us. But there's not going to be enough data. You need a lot of data. It's hard to do. So here they have, this is researchers from Zhanhang. They have performance indicators, and they determine the clusters based on some physical relationships, some engineering reasons. And then it's a Wiener process as opposed to gamma, but then it's kind of the same. See those thetas over there? They're the same. The R becomes a part of that. So as the thetas shift, the components in that cluster shift. And notice you see the alpha terms up in the upper right, same sensitivity factors. Some of them are 0 if it's not in the cluster. Okay, they gave a nice parameter estimation method. I knew I wouldn't have time for this, but also we can do this whole thing just using statistics or machine learning. And I know there's some good papers here, but I haven't summarized them. And then finally, because I've been going a whole hour, what's next? Well, I wrote some papers, 3 papers recently with Xiaoyan Zhu and students. Xiaoyan is at University Chinese Academy of Science, where we simultaneously did design optimization and maintenance optimization. My goal is to do the same thing here, except for systems of degrading components. And our decision variables, I thought it would show here. There it is. Our decision variables are this on condition. This will be a tough problem because we'll be determining design and maintenance optimization simultaneously. So system optimization based on degradation. Here's reinforcement learning with my former students, Nooshin Yousefi, now at Amazon, and Stamatis Tissinakis, now at Google. But we've written 2 papers recently using reinforcement learning. Why didn't I talk about these more? Because they don't show a strong dependent degradation pattern. And that's what my talk today is about. But we could do it. We could do it with reinforcement learning and opportunistic maintenance. I've gone late, but that completes my talk. Thank you for your patience.
Thank you, Professor. Yeah, thank you. I think Professor Coit has given us a very excellent review for classic and also some very recent and new contributions on related topics. So actually, can I ask a question first? So yeah, so it's like we actually work on maintenance and warranty models more than reliability models, but actually reliability models is the very basic thing. So we need to build on the model on it. So I'm very interested in the final papers you have introduced, like the paper written by the Yousefi. It's like, yeah, it's the reinforced dynamic maintenance policy models based on deep reinforcement learning. Yeah, like
so 2 papers. There's a brand new one, 2022, that I didn't show. I guess it has been published. So, what we're doing there, the whole idea is this, that, we think of things like inspection times and on-condition thresholds. We think of those, you fix those, this is what you traditionally think.
Yeah.
You determine the good values and use them. But what we're saying in this paper is maybe not. For example, inspection time, the next inspection time can be a variable. It depends. If the component's degradation status is they're like new, well, you don't need to inspect for a while. Now, keep in mind, the system is going to be a mixture, some old and new together.
Yeah.
And, if they were all new, it's obvious. You don't need to inspect for a while. If they're all old, it's also obvious. Inspect often. But if there's a mixture, it's not always so often. Now, if any component is very close to failure, but you haven't replaced it, you need to inspect often. But there's all these in-between stages. Now, furthermore, think about this. If you put your on-condition threshold lower, you're going to lose money because you're going to replace components that still have life in them, but you don't need to inspect as often because you can be sure. So it's a trade-off. I'm not suggesting that, by the way. I'm just saying there's always a trade-off. if I want to inspect very often, I can increase the unconditioned thresholds. Anyways, in those two papers, we treat those decisions as dynamic, meaning tell me the state of your system and I'll tell you when to inspect next, what to replace. And the rules change based on the state of the whole system, not an individual component. And so this work, in one sense, the second author was Stamatis Tissonakis, and his research and what he's doing now for Google is machine learning and reinforcement learning. So, he was the one who brought this to us and did this. The difference between our two papers, the first paper, the one I showed you, we have discrete states.
Yeah.
And we, a traditional neural network I think. But the second paper, we have continuous states. And so we use a deep learning neural network. Now, again, I don't know the specifics, but my students do.
Yeah, sure. So I want to say that there are many existing classic methods, and you can see in the literature the methods like reinforcement learning or deep reinforcement learning are emerging now in the literature. And I do think the classic methods also have some merits. Maybe the difficult point is how to combine the classic models that you have proposed in the past decades to with the data-based methods, data-driven methods to facilitate.
Yeah, let me if you're done, let me address that. I was at about 1 month ago at the RAMS conference, where the theme this year had to do with machine learning and things, it's popular everywhere. But when it comes to maintenance, when it comes to reliability, what you just said is so important. You can't ignore the traditional methods. The traditional methods are based on science. They're based on provable. So the machine learning has to integrate with the traditional methods, as opposed to replace it. And yes. Someone might say, no, I don't think that's necessary. Well, it's not necessary to write a research paper and get it published. But if you're going to get acceptance from people in organizations doing maintenance, my personal opinion is that integration is critical.
Yes.
You need to, I use the word sell, maybe that's the wrong, or promote would be a better word. You need to promote the machine learning as a way to improve upon the traditional methods, not to replace them.
Yeah, sure. Yeah. I think when we are doing future works about the maintenance or even warranty optimization problems, we need to find the merits in the traditional methods and to combine the new methods with them. Yeah, sure. So other professors and students, do you have any questions to Professor Coit?
Hi, David. How are you? Thanks
Good,
for
good.
your presentation.
Well, thank you. I was very happy to get the invitation, and
happy to see you again. It's
I-
really give us a big picture in this field. Thank you very much.
I need to apologize. I know I was talking very fast, and
I hope it will going to be common soon, and welcome to visit our team this year.
I would like to. Yeah, that's. I've learned not to predict what's going to happen, because whenever I do, I'm wrong.
Okay, thank you.
But
again.
let's hope that things improve. I was planning to, I thought, like in the later part of 2020, I thought I'd probably visit China in 2021, but of course, obviously didn't happen.
Yeah. Okay, thank you.
Okay.
Hello, Professor.
Hello, how are you?
How are you? I'm fine.
Good to see you.
Long time no see you. How about your life in New Jersey?
Well, it's now, of course, it's cold here, probably same as there, it's cold there. So, my number one hobby is bicycle riding, but I can't do it when it's cold. So, so I can feel I've gained weight. Because I need to find a new way to exercise because I haven't been able to bicycle ride. But it's life at Rutgers, life in America is returning to normal, but who knows? Who knows? Again, I can't predict. So I would say I'm doing well because I'm teaching now in person. Now, last year, all teaching was online. So as much as I understand the reasons, I don't like it. Okay, it's okay. Even last Friday, I started feeling sick. And if you're feeling sick, you're not supposed to go to the university. So I did my class online. So that's kind of nice, but I don't like online teaching.
You like face to face?
Yeah. Face to face, you can look at someone and you can tell, oh, they don't understand. Or so I look forward to when everything returns to normal. Well, probably won't ever return completely to normal, but close.
Yeah, me too.
Yeah. Okay, thank you. Good to see you.
Thank you for your seminar.
Yes, well, I as I say, it's a pleasure. It's I've visited many universities in China, all over the country. But the time I visited Tianjin University, one very happy memory.
You are the half Chinese. Yeah.
No, you need to teach me. You need to teach me to speak. Next year.
Okay, thank you, David. Thank you very much for your wonderful presentation. One question for your study. You know that in China we have a lot of automobile companies producing electric cars, and the battery for the automobile industry is very important, because some Chinese big companies like the one in Fujian province, the largest manufacturer of the battery. So have you studied the degrading problem for the electric battery for the
I
vehicle?
have not myself, but right down the hallway from me, we have a student and an advisor who not only study it, but that's one of their primary research. So to answer your question, no, I have not. But within our department at Rutgers, we have a young professor who's not only studies it, but that's his primary research area. So I can't share any insights myself, but I know that just like in China, it's considered very important, and many people working on it.
Yeah, I mean that these companies really require some expert to help them to build the reliability models to predict the life of their battery.
Yeah, well, I know from my phone, I'm going to get a new phone only because of the battery. I kind of like the phone, but it only will last now about an hour and a half before I need a charge.
Okay, anyway, thank you so much.
I think a lot of degradation studies on batteries actually borrow a lot of ideas from traditional reliability or degradation models, but they need to combine their domain knowledge into the model. those. So that may be also a very challenging thing. And that the upside is that they can collect data because there are battery management systems that can provide data online. Yeah, actually, this may be their advantage in doing this.
Yeah.
Yes. Yeah. Okay. So do others have any questions or?
Well, also let me say that you know, the professors here have my email, and so I don't mind at all. You know, someone wants to send me a email, and you know, pretty much, you know, ask for anything. Question. I mean, mostly question on my talk today, but if someone had another question, they're certainly welcome to. You know, I'm busy like everyone else, but you know, I always like it, like most professors, if someone's interested in my research.
Yeah, sure.
Yeah.
I think
So you
because
can tell that
you have so many works, and maybe so many people are interested in we have cited I think on average when we are doing degradation, we cite maybe 3 or 4
Good.
to 10
Keep it up.
papers from you in each paper.
But I remember when I was a graduate student or a new professor, you know, sometimes I would email some famous professor and I thought, oh, they're not gonna, you know, they'll never answer.
Okay.
But if you show interest in somebody's research, they often will. They often will.
Yeah,
I was somewhat surprised. You know, I'd get an email right away sometimes from, you know.
Yes. Yeah. So if others don't have any questions, so we would like to thank Professor Coit again for the very interesting talk. And if you have future questions, you can contact me or Professor anytime. I think Professor Coit is very nice. He's regarded one of the nicest professors in our field.
Oh, that's probably not true, but he'll tell you the truth later.
Yeah, and Professor Coit is also a very frequent visitor to China in the last decade because of the situation. So it's not possible now, but I hope that you can visit Tianjin.
Yeah, before COVID, I visited China 10 straight years. 10 straight years.
Yeah.
You know,
Sure.
Including, you know, 2019, I was there 2 months. 2014, I was there over 2 months. You know, and
yeah. Sure.
Okay.
Let's
right.
thank Professor Coit again. Thank you.
Thank you.
Thank you.
Yeah, thank you.
Okay.
Thank you, David.
Goodbye, everyone.
Okay, bye-bye.
Goodbye.
Stay
Bye-bye.
healthy.
Thank you. Bye bye.